Okay, so after a very long pause, I have returned. So let's just jump straight into this next problem, 3.10. Is the ground state of the infinite square well an eigenfunction of momentum? If so, what is its momentum? If not, why not? So, what is this asking us? Let's see. It's basically asking us whether or not we can properly apply the infinite square well ground state wave function into the eigenvalue expression that we've been working with for this entire section. So remember what the eigenvalue equation is. It's basically that some operator, let's call it a hat, and I have a new tablet, and it feels a little bit shaky. I'm not entirely familiar with it yet, so please forgive the slightly messier handwriting. But it's basically telling us that when we act an operator, a hat, onto our wave function, psi of x, we're going to get some eigenvalue for our operator, let's call it a, times that same wave function, psi of x. So in this case, we are asked to take psi of x and replace it with the wave function for the ground state infinite square well. Well, we know that the infinite square well has the wave function psi n of x is equal to the square root of 2 over a multiplied by sine of n pi x. Whoops, that's a horrible pi. I'm sorry. N pi x divided by a, where a is the width of your infinite square well. So our ground state wave function is going to be just applying n equals to 1. So psi 1 of x is going to equal the square root of 2 over a multiplied by sine of pi x divided by a. So then, at this point, let's try plugging it into here. So remember, we're trying to find whether or not momentum is a valid eigenfunction of this wave function. So our operator of interest in this case is p hat. So p hat times psi 1 of x, well, this is equal to, remember, momentum has the operator itself is defined as negative I h bar d by dx. So if we then apply this to our psi 1 wave function, this is going to give us square root of 2 over a times sine of pi x over a. And we are asking whether or not this is going to give us some constant that we're going to call p, which is our proposed eigenvalue, multiplied by our same psi 1 expression, which is, what we just written out here. Square root 2 over a times sine pi x over a. And very obviously this doesn't, right? If you take the derivative of a sine, you're going to end up with a cosine. There's no way to get a cosine to equal that sine generally. So this tells you that this is not equal to this. Therefore, momentum is not an eigenfunction of the infinite square well ground state. And in fact, more generally, right? Because remember, all of your higher energy states are just sinusoids, right? This means that momentum just isn't a valid eigenfunction for any of the infinite square well states. We can take this even further and say, well, via sort of, completeness theorem, right? Any wave function can be expressed as sort of this infinite sum of infinite square well wave functions, right? Any arbitrary wave function, psi, can be equivalent to the sum from n equals 1 all the way to infinity of square root 2 over a times sine of n pi x over a. And, if you take the derivative of this, all of your sine terms, you're going to have a sine of pi x over a, a sine of 2 pi x over a, sine of 3 pi x over a. Those are all going to turn into cosines. So therefore, generally, right, for any wave function, momentum is not a valid eigenfunction for any wave function. Now, what is the actual physical significance of this, right? So remember that earlier in this chapter, what we said was that effectively, if an operator has an eigenfunction that actually is valid, right? If an operator has some sort of eigenfunction for some wave function, what that means is that that operator is sort of a determinate state for that respective wave function. An example of this is energy. Energy is an eigenfunction of the infinite square well. What that means is that energy is a determinate state when you measure it in the infinite square well, right? Energy, when you measure it, is going to equal some specific value. In contrast, if it's not a valid eigenfunction like momentum, right, in that case, it's not a determinate state. So if it's not a determinate state, that means that you cannot say that, P has some specific value, right? It doesn't make sense in quantum mechanics to say that momentum is constrained to some specific numerical value. Instead, you have to say that momentum has some probability of being in some range, dp. And that's pretty much consistent with what we've been talking about or observing since chapter 1, right? Quantum mechanics has built-in indeterminacy. Things like position and momentum tend to be indeterminate. So as a result of that, that sort of what we've been talking about this whole time about indeterminacy of momentum, position, and a bunch of other things, we're seeing that here in that, something like the momentum operator isn't actually a valid eigenfunction for our wave functions. So because of that, it is therefore indeterminate, and we come sort of into this cyclical argument. So I'm going to stop, going around in circles. But that is effectively the solution to problem 3.10. Okay, I just realized that I skipped problem 3.9. Honestly, I'm tempted to just skip it just because of how simple of a problem it is, but let's just do it just for the sake of having a complete set, right? So part A, cite a Hamiltonian from chapter 2 other than the harmonic oscillator that has only a discrete spectrum. So let's look at this, systematically, because I can just list one arbitrarily, but that's not going to help us that much in actually understanding the problem on a slightly deeper level. So we analyzed 5 different systems in chapter 2. Let's list them all out right now. So number 1, we have the infinite square well. Number 2, we have the harmonic oscillator. Number 3, we have the free particle. Number 4, we have the delta well. And then number 5, we have the finite well. So what does it mean to find a Hamiltonian that has a discrete spectrum? Discrete means, actual numerical values that are not just in some range, right? So we're trying, what this problem is asking us is find one of these systems and represent which one it is other than the simple harmonic oscillator that has discrete values for energy. Well, let's just go down the list. Literally number 1, right? The energy for the infinite square well is equal to n squared pi squared h bar squared divided by 2m a squared, right? It's literally just that. So just like that, we've finished problem 3.9a. So let's move on to part B. Okay, one of the reasons I don't really like this problem is because B is I feel like it's a bit stupid. Cite a Hamiltonian from chapter 2 other than the free particle that only has a continuous spectrum. So we know that the free particle has a continuous spectrum because, it represents a free particle. It can have any arbitrary energy it wants. So because of that, it's not just limited to specific values as denoted, by some index n. But, all of these other ones technically are not only continuous. Infinite square well and simple harmonic oscillator, these two, sure, yeah, these are only discrete. Free particle is only continuous. Delta well and finite well, they're not technically only continuous, right? For both of these, if your energy is larger than, sort of the potential of the well, then it becomes a free particle and it's continuous. But if your energy is lower than the well, then you're stuck in the well. You have a not continuous spectrum instead. You have a discrete spectrum. In a delta well, you actually only have one specific possible value for energy in the case where you have a bound state, whereas in a finite well, right, if you're stuck in it, then it's the same thing as an infinite square well, but like a slightly different expression. So I'm not sure if maybe this is a typo, but either way, let's just study a specific case scenario, in which case it would be the delta well, but only for scattering states. However, if we're looking at just any specific system that is always going to be continuous no matter what output or no matter what values the energy actually takes, it's just going to be the free particle. There's no other one in this set that has only a continuous spectrum. Okay, and then for part C, both discrete and continuous, well, we just covered this in part B, it's both the delta well and the finite well. They want to exclude the finite well, so we're sticking with the delta well. So the delta well has two possible cases. Number one, scattering states, where your energy is big enough that you can escape the delta well, in which case you're basically just looking at a free particle, which has continuous states, right? Or not continuous states, but a continuous spectrum for the Hamiltonian. And in the case where your energy is not high enough to escape the delta well, then it's basically a bound state stuck in that delta well, in which case your energy is only one possible value. So because of that, the delta well is the system in this case for part C that has both a discrete and continuous part to its spectrum.